Mr. True, in this video we're going to be doing 4 examples where we're introduced to the concept of a definite integral. Now this is for my AP Calculus A, B, and BC classes. We do not need to analyze definite integrals with a limit of sums. If that's what you're looking for, you'll in the description find a link to that process and type of problem. This is just an overview of the definition of a definite integral and how we're going to need to analyze and use this in AP Calculus. We're going to be doing basically estimating the area under this curve using left and right Riemann sums, ultimately estimating this area under the curve y is equal to 2x between the values of 1 and 7 using 3 rectangles. That'll be left, right, and midpoint Riemann sum. Then we're going to move on to an overview of what you'll see in the next section of your calculus book probably, it is in the one I teach from, finding areas of common geometric regions or evaluating definite integrals with the recognition that the region you're trying to find the area of is something you learned how to calculate in geometry. And then we'll move into what would probably be in the next section of your calculus book, which is evaluating definite integrals, sort of the quick way, actually using integration and that definite integral notation to most efficiently and quickly evaluate a definite integral. And we're just giving you I'm trying to give you an overview of what's happening in the next 3 sections of your calculus book, because I remember when I started relearning calculus after 20 plus years of not seeing it, it felt like I kept seeing the same thing over and over and over again, and I didn't really understand the big picture until I was done with the entire chapter. So I'm going to try and give my class and you that big picture right now. Okay, so we're going to first try and estimate the area below the curve of y is equal to 2x and the x-axis between the value or on the closed interval from 1 to 7. Definite integrals, by the way, have many applications beyond just evaluating or finding area between a curve and the x-axis. And if that curve goes below the x-axis, well then the quote-unquote area may seem to be a negative number, but that negativeness of the area would just be the identification that is below the x-axis as opposed to above the x-axis. But again, you might be talking about acceleration and volume of particles, production at the end of an assembly line, any kind of business applications. It's not just about area. We're just looking at this concept in the realm of geometry, just like we did when we started with working with derivatives. So Riemann sum. What the heck is that? It is the idea that we're going to estimate this area with a sum of common geometric regions. And most commonly those regions are in the shapes of rectangles and trapezoids. We're going to focus mainly on rectangles today. You'll see why when we get into actually being given the definition of a definite integral. But it's just a sum of common geometric regions. And well, the lowest number of common geometric regions we can use is 1. And if I just simply draw one rectangle, now I'm going to start at the x value of 1, and I'm going to bring this rectangle up until the upper left-hand corner touches the function, and then just go all the way over to 7 and say, I'm going to let this one rectangle be my estimation for the area under the curve, or it's a linear function, but the curve y is equal to 2x and the x-axis. And we can see that that one singular rectangle is going to miss a lot of area. It's definitely going to underestimate the area between the curve and the x-axis. Now, the reason why the left Riemann sum is going to underestimate the area under the curve y equals 2x and the x-axis is because on this domain, and this is a constant line, so its entire domain, this function is called monotonic increasing. The slope is always positive. And if a function is increasing, well then that left Riemann sum will always underestimate the area under the curve. And complementary to that, the right Riemann sum, if I draw a single rectangle where I let the x value of 7 or the right-hand side of this region define the height of my rectangle, I'm going to get what you could guess is going to be a massively overestimation of the area under the curve. So we have a small orange rectangle and we have a large blue rectangle, and we have the actual area shaded in white. If a function is decreasing, well then the left endpoint is going, a left Riemann sum is going to make an area which is too big as opposed to underestimate the area, it'll be an overestimation. So my example is about an increasing function throughout its entire domain. So the left Riemann sum is always going to be an underestimation or a lower sum, and the right Riemann sum is going to be an upper sum or an overestimation. Don't be confused though with left Riemann sum is not interchangeable with lower sum or even upper sum for that matter. Being asked to find a lower and upper sum is not the same as being asked for a left or right Riemann sum. A lower sum means that every rectangle that you use, if that's your common geometric region, has to be an underestimation of the area, and every rectangle that you use has to be an overestimation for an upper sum. Okay, well, one rectangle is clearly not going to be a very good Riemann sum, a very good approximation of this area that I've shaded in white. So maybe instead of using one rectangle, we use two. And the distance between 1 and 7 is 6, and if we take 6 and divide it by 2, we get a distance of 3. So maybe we go from 1 to 4 and make a rectangle, and then from 4 to 7 and make another rectangle. And in orange, I'm letting the upper left-hand corner of each of these rectangles stop at the function itself. Or in other words, the x value of 1 is getting plugged into the function y equals 2x, and that y value becomes the height of this first rectangle, and we plug 4 into 2x, well then we get that height of 8, or that y value of 8, determining the height of that rectangle. And now we have two rectangles that, at least drawn, are estimating the area into the curve. And look at all this extra area we picked up. All that area between 4 and 7 and 2 and 8 have been picked up now. So what is that? 3 times 6, so 18 additional square units of area have been picked up by this left Riemann sum. So clearly, and if we can do the same with the right Riemann sum, go to 7 up and over 3, let that go all the way down, and then have that interval from 1 to 4, go to 4, go to that right side of the interval of 4, 4 times 2 is 8, and get that height, and have lost that same amount of area, that same amount of overestimation. So the more rectangles we draw, the more subdivisions we create within our region, the better our approximation is going to be of this estimation of area. Just like when we found we talked about derivatives and the slope of the tangent line. It's really a slope of a secant line. It's just that those 2 points get so close together, it's indistinguishable. But again, in just AP calculus, we don't have to do a limit of sums up process. I'm just introducing the concept in 3 different fashions that we're going to be introduced to the idea, the concept of definite integrals, and Riemann sums for that matter. Doing Riemann sums with a finite number of rectangles. Now what I want to really walk through is a Riemann sum with 3 rectangles, a left Riemann sum. So again, that distance between 1 and 7 is a distance of 6. 6 divided by 3 is 2. So we're going to have a subdivision or a rectangle that goes from 1 to 3, a rectangle that goes from 3 to 5, and a rectangle that goes from 5 to 7. So each base of each rectangle is going to be the same value of 2. Now when you do Riemann sums in calculus, truly you don't have to have equal intervals, equal, say in this case, delta x's as we set up our Riemann sums. It's just being done for convenience, and it's what is most commonly done. So we're going to take the value of 1, allow it to determine the height of this rectangle, and then go over 2 units. The value of 3 to get plugged into y equals 2x and determine a height of a rectangle and go over 2 units. And then the same with 5. So a Riemann sum, a left Riemann sum with 3 subintervals is going to be equal to f of 1 times that width of 2 plus f of 3 times that width of 2 plus f of 5 times that width of 2. Now I came up with a very easy example, and we are doing the same function of y equals 2x through all 3 of these ways of evaluating area. This is just an overview, again, a big picture. We can see that these values are 2, 6, and 10, but just to work it out, we have 2 times 1 times 2. We have 2 times 3 times 2, and 2 times 5 times 2. We have 2 times 2, which is 4, 2 times 3, which is 6, times 2, which is 12, 2 times 2 is 4, times 2 is 5, is 20. And so our left Riemann sum is estimating the area under the curve y equals 2x and the x-axis, or between the curve of 2x, y equals 2x and the x-axis, to be 20, 30, 32, 36 square units. Now, ultimately, we're building up to the idea of defining and understanding what definite integrals give us. They, again, have many more applications than just area. So when we get an answer from a definite integral, not that you have seen me write a definite integral yet, please do not just default to a square units. Use the units appropriate for your particular problem. A right Riemann sum, an estimation of this area under the curve between 1 and 7 underneath 2x, y equals 2x, using right Riemann sums means that we're going to have bases which have, or rectangles that have a base of 2 again, but instead of letting the values of 1, 3, and 5 determine the height of these rectangles, we're going to let the values of 3, 5, and 7. And just by looking at the picture, we have a base of 2, and we're going to go up and let the right-hand side touch. We have a base length of 2, and we're going to let the right-hand side of the rectangle go up and touch. A base of 2, and let the right-hand side of the rectangle go up and touch. And the picture is kind of giving us an idea of what's going on. Our right Riemann sum is going to be equal to 3 getting put into the function 2x and getting a height of, well, 3 times 2, or 2 times 3 is 6 times its base of 2. Then we're going to take the x value of 5 and plug it into our function. So f of 5 times the base of 2, and f of 7 times the base of 2. Giving us a height of 6 times 2, which is 12. Well, height of 6 times the base of 2 is an area of 12 for our first rectangle. We have a height of 10 times the base of 2, which is an area of 20 for our second rectangle. And 2 times 7 is 14 times 2, which is an area of 28 for our third rectangle, giving us a right Riemann sum, which is equal to 20, 40, 50, 52, 60 square units. Now, I do want to talk about estimating the area between the curve y equals 2x and the x-axis between 1 and 7 using a midpoint Riemann sum, but I want to save that for just a moment. Well, actually, there's no reason for me to do that. Let's go ahead and do that. So we're going to now use a midpoint Riemann sum. I was kind of pausing because this is a linear function. And because of that, you're going to see some specialness between these left and right Riemann sums, but maybe it's, well, you're going to find out in a minute. We're going to let the midpoint value of not 1, 3, and 5, not 3, 5, and 7, but the x value that's in the middle of those intervals determine the height of these rectangles and do a midpoint Riemann sum, which actually now I am going to come back to that in a minute. I want to use what work I have up here to help us build the actual definition of a definite integral. You know, what's actually going on here? Well, understand that I'm about to build up the formula for the definition of a definite integral. My book calls it the first fundamental theorem of calculus. I've seen books where they sort of change the order of the names. So neither here nor there. We came up with a left and right Riemann sum with only 3 subintervals without seeing all this fanciness that we're about to come up with. While we don't need to do a limit of sums, calculate definite integrals using a limit of sums process in AP Calc, we do need to know the definition of a definite integral. They'll give us questions, and that'll be the last example in our video where we see how AP may possibly test our knowledge, our memorization and understanding of the definition of a definite integral, the first fundamental theorem of calculus. So make sure you put that to memory. And the creation of this definition, if you forget it, or maybe some of its parts, think about how we're about to develop it right now with our sort of basic geometric work we just did using 3 subintervals. Now, anytime in math that you have seen repeated addition over and over and over again, there's a Greek symbol that represents to add repetitively. That's sigma. So we have sigma. Now, when we introduce the Greek idea of sigma, we have to have a lower and upper limit. Well, that's going to be defined, and I'm using the notation, the definition that's in my book. If yours varies differently that you're learning from, it can. But we're going to have our lower counting value, our lower limit of the sigma notation start at 1. I starts at 1. And it's going to go to n. Now, what is it that we're constantly adding over and over and over again? Well, we're adding the area of a rectangle. We're adding a value that we're getting from a function, and we're going to call the numbers that we're plugging into that function a c sub I. It's just a value of x. And then from the y value that we're getting from the function, we're multiplying it by some, well, in this case, constant value of 2, but that was some predetermined interval spaces along the x-axis. Or in other words, we're talking about a delta or change in x, which for convenience sake and really to be in line with what my students will see on the AP Calculus exams, those delta x intervals, the widths of each of those common geometric regions are the same. They don't have to be. Now, we looked at how much of an over or underestimation what one rectangle would have made. We saw how much better 2 was, and then we worked with 3 rectangles, and indeed, the more number, as the number of those rectangles increase, the better this approximation will be for area. So this part we don't really have to do, for better or worse. Estimating a definite integral using a limit of sums is that process that, well, we have to be aware of. In AP Calc, we don't actually have to do. And this is going to be equal to the definite integral from a to b of f of x dx. You may see this in your book when you get first introduced to this idea of Riemann sums. It ultimately comes into full power and full revelation maybe 3 sections later, if it's like the book that I'm teaching from, where we get to sort of skip the long, arduous limit of sums process and just jump right into the fast way of finding antiderivatives and then working through this definite integration process, which is going to be equal to capital F of x with an upper limit of b and a, and I'm running out of space here, but then that's equal to f of b minus f of a. And all of this is your definition of a definite integral. Really, your book might be just highlighting these first 2 pieces here. But to really understand all the pieces here, we have some pieces left. What the heck is c sub I? Which I just wrote c sub 1, but what is c sub I? C sub I is just a value of x that you're plugging into a function. And we first plugged in 3, and then 5, and then 7 with a right Riemann sum, and we plugged in the values of 1, 3, and 5 with the left Riemann sum. Well, c sub I is just a combination of knowing where along the leftmost side of the x-axis, what's the lowest or farthest to the left border of your region. Where do you start collecting the area? And by the way, you can integrate with respect to the y-axis as well. It just works out the same, but we're working with this y equals 2x through all 3 parts or 3 ways of evaluating definite integrals. You start with 1, and then you move some delta x. And then you move that delta x again and again. So c sub I is basically some kind of recognition of where along the x-axis do you start moving? How far do you move each time? And how many times, this is where the I comes in, how many times I are you going to move, in this case along the x-axis, could be along the y-axis, from your lower limit of A. Now, I has to start at 1, and our picture started at 1. Well, with a right Riemann sum, the first x value that we plugged in was 3. We found that delta x, let's do that real quick. We found that delta x. What did I say how did I calculate the fact that we were going to move 2 units every time? I said the distance between 1 and 7 was 6. Delta x is a difference of b minus a, and then we were going to do a right and left Riemann sum with 3 rectangles, where n is the number of those rectangles that you're working with. Which I'm going to say is the number of regions, not number of rectangles, because you might be doing a Riemann sum with trapezoidal sum instead of a rectangular sum. So we had that lower limit of 1, but our numbers were 3, 5, and 7. So when I was 1, which is where our lower limit of the sigma starts working with, it was like I is 1, you're working with 1 rectangle, well then immediately move 2 units off of 1. And then move 2 units off of 1 twice, and then move 2 units off of 1 3 times. So I is that counting number, starts at 1 and goes up by 1 until you get to n, the number of rectangles that you're using to estimate your area. And for a right Riemann sum, this is the formula. C sub I is A plus delta x times I. Well, for a left Riemann sum, we actually use the lower limit, or the farthest left value of x within our interval of 1, and then we counted by 2, and then we counted by 2 again. So remembering that I has to start at 1 by definition, yet we didn't do A plus or 1 plus 2 times, or anything, 1 plus 2, yeah. We didn't move at all. We didn't move horizontally at all off of A, or in this case, our lower limit was 1, with a left Riemann sum. So C sub I, for a left Riemann sum, has to have some kind of addition to this expression that says, don't move that first step when I is 1. So it's A plus delta x times I minus 1. So here's all the pieces to the definition of a definite integral. Pieces which will come into more interesting play if you're doing that limit of sums process, but all of this will need to be understood for when AP is going to test our knowledge of the definition of a definite integral, or that first fundamental theorem of calculus. Even though we didn't know any of this, or we're not aware of any of all this fancy looking notation, when we were told to estimate the area below y equals 2x, or between y equals 2x and the x-axis between the regions of 1 and 7. So that's the idea of left and right Riemann sum, and how that work can help you recreate some parts of that definition if you happen to have forgotten some little bit of it. Now, a midpoint Riemann sum simply says to not use the left or the right endpoints of each interval between A and B, but use the midpoint. So if we have from 1 to 7 is 6 units, and our rectangles go from 1 to 3, from 3 to 5, and from 5 to 7, just allow the x values in the middle to be the ones that determine the height of the rectangle. So we have a height of a rectangle that's going to be determined by f of 2, and then f of 4, and then f of 6. And our midpoint Riemann sum would be, therefore, not f of 1, not f of 3, but f of 2 times 2 plus f of 4, because I'm counting by 2. Each rectangle has a width of 2, times 2 plus f of 6 times 2. That's going to come out, just so you can see a nice what's going on here between left, right, and midpoint Riemann sum. We have f of 2. 2 times 2 is 4. Times 2 is 8. We have f of 4. 4 times 2 is 8. Plus 2 is 16. And then we have f of 6. Well, 2 times 6 is 12. And 12 times 2 is 48. Right? No. 6 times 2 is 12. 12 times 2 is 24. Added one more extra multiplication of 2. And we have 10 and 20 is 30. Now we have 36. Now we have 40. And now we have 48. Now, because y equals 2x is a linear function, you're about to find out that 48 is actually the area between y equals 2x and the function between the values of 1 and 7, because we're going to move on to finding this area with the recognition that this is a common geometric region. And also you might realize that if you do 60 plus 36 and you get 96, and you divide that by 2, you get 48. So a midpoint Riemann sum is an average of the left and right Riemann sum. Do not expect, however, the midpoint sum to ever be equal to the actual area under the curve. That's just going to be a phenomenon for this question because our function that I'm using to introduce all this is a linear function. Okay, so hopefully you now understand about estimating area using a finite number of rectangles with a Riemann sum. So common geometric region. So you're given this problem of evaluating the definite integral from 1 to 7 of 2x dx. Now you can estimate it using a few rectangles or more, but if you go to evaluate a definite integral, you are expected and encouraged, if not required, I guess I just said that by saying that you're expected to, but you can make your life a lot easier with certain integration problems in calculus if you recognize that the region which you're trying to find is a region that you learned how to find the area of in geometry. I mean, you need to recognize that one application of definite integrals is to find area between a curve and the x-axis. If that function is linear, like a y equals 2x, or maybe if you have a definite integral from a to b of an absolute value function, and it could be with respect to x or y, where the inside function is a linear function. These should be both giving you the idea that maybe you could evaluate this area with the area of a triangle or trapezoid formula, or maybe a rectangular formula. If you have a definite integral from a to b and your integrand is a square root with a difference of squares, one of these are going to be a function and one of these are going to be a constant. That is an identification that, it's probably going to be the second one, that's going to be an indication that you have a common geometric region which is a circle, right? If you have something like x squared plus y squared is equal to 4, that's the equation of a circle whose center is at the origin and whose radius is 2. Well, that's y squared is equal to 4 minus x squared, or y is equal to plus or minus the square root of 4 minus x squared. Well, we know how to find the area of a circle. It's pi r squared. And if we only want half a circle, of course, it's going to be 1/2 of pi r squared. And whenever we can save time by recognizing that our definite integral involves an integrand, which creates a common geometric region, you can save yourself some considerable time. We have here this y equals 2x between 1 and 7 is creating the shape of a trapezoid. And we know how to find the area of a trapezoid. We have two parallel sides, which are going to be considered the bases. And then we have a line segment, which is perpendicular to those two parallel sides. So indeed, the area of a trapezoid is 1/2 the height times base 1 plus base of 2. So with the recognition that we have a trapezoid here, it is perfectly viable after setting up the definite integral using the proper upper and lower limits to say that that's equal to, not approximately equal to, this isn't going to be an over or underestimated value. It's going to be equal to 1/2 the height. Well, that segment length that is between the two bases, those two vertical parallel segments, the length between 1 and 7 is going to be 6. And then that's going to be times the height of this side, which is what we get when we plug the value of 1 into our function. So base of 1, or b sub 1, is 2 times 1 plus b sub 2, and the 2 is from the function y equals 2x. b sub 1 plus b sub 2. The height of, or the length of this segment that we get from plugging 7 into the function y equals 2x. So we have half of 6, which is 3, times 2 times 1, which is 2, plus 2 times 7, which is 14. So we're looking 3 times 16, which is equal to 48. And I'm doing square units because I know this definite integral problem is specifically applied to a area application. Square units may not make sense for some other definite integration problem. Now, once you get through the section that introduces the concept of a definite integral and Riemann sum and introduces that definition of a definite integral, and then you roll through a section of evaluating definite integrals using common geometric regions, well, then you're going to just start getting problems that expect you to go through that definite integral process, which is to say that the definite integral from a to b of f of x dx is equal to, first, apply what you just learned about finding antiderivatives, find the antiderivative of lowercase f, and get that uppercase f. Keep that upper and lower limit of b and a, and then just simply plug each of those values into your antiderivative and subtract. So first plug in your upper limit. So we have capital F of b minus capital F of a, and that is going to be, in this case, again, finding the area between the curve y equals 2x and the x-axis. But the number that you get from a definite integral is definitely not always, in terms of application problems, going to represent area. So the definite integral from 1 to 7 of 2x dx, see, f of x or f of c sub I, kind of like from that definition of a definite integral, and here's like our calculus representation of delta x. Now when we go to integrate and evaluate this definite integral, the value of 2 is a constant coefficient. We know that from the properties of definite integrals and actually just integration in general, you can bring that constant coefficient out front and say that that's equal to 2 times the definite integral from 1 to 7 of x dx. Now your integrand is a variable base with a fixed exponent. We can increase that exponent by 1 and then divide by that increased exponent using that power rule for integration. We have an upper limit of 7, a lower limit of 1. And in front of this x squared, we have a coefficient of 1/2. We can go ahead and bring that out, which I like to do before plugging in the upper and lower limits to simplify my arithmetic. So we have 2 times 1/2 times, now we're going to plug 7 into our antiderivative, or plug 7 into x squared, minus, then plug in the lower limit of 1 into x squared, the x squared that we got from integrating 2x. Half of 2 is 1, so these are going to cancel out. That's why I'm pausing on that x squared part. We have 7 squared is 49, and 1 squared is 1, and 49 minus 1 is, again, 48. Now, one more time, this is a linear function. That would be the only situation where your midpoint Riemann sum is going to give you the exact value answer. Your midpoint Riemann sums are still an estimation of the actual area. This is an exact approximation of the area that we're getting from the definite integral, because of course that is equal to that limit where the number of rectangles went to infinity. Excellent. Now, that's the three stages or sections that will be introducing the definition of a definite integral, the first fundamental theorem of calculus. And again, I'm just doing this whole big picture because when I remember relearning calculus to get ready to teach this course, I just felt like I kept seeing the same thing in the book over and over and over again. I did not understand why it kind of kept saying the same thing slightly differently, but seemingly the same thing over and over and over again. So getting out of this introduction based off of the function y equals 2x, how may calculus, AP test your knowledge, your memory, your understanding of this definition of a definite integral? It could very well be in some type of limit statement that initially, if you don't know this definition of a definite integral, it's going to seem very daunting, if not impossible. Something like this. You may go to your test and see this limit statement that you remember, well, man, I studied limits. I was introduced to limits in chapter 1, where we analyzed them analytically, and maybe a little bit later in your book you learned something called L'Hopital's rule, and man, this looks nothing like any of those questions. How the heck are you supposed to do this incredibly complicated looking limit statement? Well, you're kind of but you're not going to evaluate, at least you're not going to evaluate this expression with the way it looks right now, because that is just disgusting looking. But limit as n approaches infinity. Limit as n approaches infinity. Well, that's not unique, except now it's in front of a sigma notation where I starts at 1 and goes to n. Oh, that's exactly the same as your definition of a definite integral, that limit of sigma notation, or the limit of sums. You have an f times c sub I and a delta x. So after the sigma notation, start looking for the two parts and start identifying what's the function, what's c sub I, or what's going to be that lower limit for the definite integral. It's that recognition of what this is so that you can then set up the definite integral and finish the question, honestly, quite easily. You have this 4 over n. Well, delta x is b minus a over n. So you've got delta x is equal to 4 over n. So if you can pull that out, you'll realize this is basically like your delta x, which ultimately, in terms of your definite integral, is going to be your dx. Well, if you've identified basically what's dx, what's your function? And with your definition of a definite integral in that limit of sums process, your function's like a composition. It's a c sub I expression getting plugged into your function notation. Well, your composition is right here. You have your 3 plus 4 over ni, a c sub I, which is a plus delta x sub I, at least if it's a right Riemann sum. So your expression inside here of 3 plus 4 over ni, well, there's your identification that a is equal to 3. Your lower limit of your definite integral is going to be 3. And how far from that lower limit do you travel to get to your upper limit? You travel 4 units. So that means that b is going to be 4 greater than 3, which is equal to 7. And what is this composition going into? Or what's the, we have the inside function of 3 plus 4 over ni. That's getting plugged into the function. The overall outside framework is something cubed. So this limit statement with the recognition that it's the left-hand side of the definition of a definite integral is equal to the definite integral from 3 to 7 of x cubed dx. And then we're going to be able to take that power, increase it by 1, and then divide by that increased power with your upper limit of 7 and 3 still in play. Now that we've found the antiderivative, we plug in the upper limit. So we have 7 to the 4th over 4, and then we do subtraction. We plug in our lower limit, and we have 3 to the 4th over 4, and then whatever that comes out to is going to be our final answer. So, yeah, okay, it's a little bit of a long video. I hope that you got all the way through it and you understand the big picture of what you're about to see in the next 3 sections of your book. I've effectively just introduced 3 sections of your calculus book all at the same time, using the simple function of y is equal to 2x. In the description below, I'll have links to videos for each specific type of topic of 4.2, 4.3, and 4.4. At least that's how they are laid out in my book of Riemann sums, common geometric regions, and actually evaluating in general definite integrals. I hope the big picture helps. It certainly is something I was lacking when I first relearned calculus to get prepared to teach it to my kids in high school. And so I hope this big long introduction, seeing everything connects together, helps you understand what's going on. I'm Mr. True. Bam! Go do your homework.